All right, good morning. It's time for us to get started. So this is our third to last lecture. So sad. So my hope is to have new material covered by Wednesday. There might be a slight bleed into Friday, but my goal is to try to have everything done by Wednesday. Just a reminder, some extra credit opportunities at the end of the semester. So evaluations for Brian, Melissa, myself in the course, worth 1 point. And we really do value the feedback, so that's important. And then there'll be an in-class quiz on Friday that's performance-based, and you can get up to 4 points added to your exam scores. So this Thursday is going to be the optional standardized exam, so it'll be in 12:10, starting at 6:30, and we'll let you run till 8:30 on that. And then a few of you have an alternative time and place, and I'll send emails out about that whenever I get a chance. I also wanted to give everybody a heads up. I'm out of town on Monday. I'm coming back Monday, but I'm not sure what time, and so I can't guarantee that I'll be around for my office hours on Monday. I will keep you informed if I will be in the office. Yeah? It should be graded by Friday morning. That's the goal. That's the goal. All right, and the final exam is on Tuesday and Wednesday. And my plan, because sometimes people are a little worried that those that take it late in the week are going to have the benefit of information from people that took it earlier in the week. So help offset that and make sure everybody's on the same level playing field. On Monday, I'll be sending an email out that just tells you what, not precisely what's on it, but it'll say this kind of question, that kind of question, know this, know that, right? So that sort of the kind of thing that you would say at the end of the exam. Oh, I didn't get this question on entropy change for expansion of an isothermal gas or whatever, right? There was a question back here. No, you got it? Okay. All right. So we've already talked about benefits of taking the multiple choice exam, so we'll not worry about that now. All right, so yes, sir.
Do you have examples of previous final exams?
So I do and I don't. I do and I don't. So if you go online on the study materials for the final, right, in the last quarter, there is an example of, so there's old finals posted. I'm not sure whether I have 1 or 2 posted. So let me talk a little bit about that. How many people have looked at those? Anybody? So you see that they're in 2 parts, cumulative and more recent. I went away from having 2 parts. So the exam's going to look like those, but just combined into a single one, and probably be a little shorter than the sample ones that are up there. Right? Does that make sense? Okay. All right. So what we did last time, we talked about delta G of mixing for ideal solutions. And what we found was that we had the same expression for the mixing of an ideal liquid solution as we saw for the mixing of gases that behave ideally, right? And for the same reasons, we see that the delta G is always negative. So we expect that if we have 2 different liquids that we bring together, if their interactions are the same together as they are isolated, we expect spontaneity for the mixing. Right? Once we had the expression for delta G, then we could determine delta S for mixing. We found that that's always positive. Right? We talked about delta V, that came out to be equal to 0, and delta H came out to be 0. And this is really, sort of the summary of what is meant by an ideal solution. You have the same interactions between the solvent molecules and the solvent-solute molecules. Right? All right. We also saw an application of the Gibbs-Duhem equation. Basically, if we know the pressure of one of our components, we can calculate the other one using this Gibbs-Duhem equation. All right. We also took a little bit of time to talk about non-ideal solutions and the impact that it has on the total vapor pressure of the solution. So we no longer have a linear relationship between mole fraction and the total vapor pressure. So we either saw that it went up or that it went down. If it went up, if the total vapor pressure went up compared to ideal, that meant that we had disruptive interactions, weaker interactions between the solvent and the solute. And if we saw a dip in that vapor pressure curve, that meant when I put the components together, they were more attractive, there was a stronger attractive interaction than the isolated solvents, right? And then the impact that this has on vapor, because there's an impact on vapor pressure, that leads to an impact on the boiling point, right? And what we saw was that because we have this elevated curve or this depressed curve for the pressure, that gave us a crossover point where the vapor phase and the liquid phase have the same composition. That's called an azeotrope. And that limits our ability to separate by distillation, right? And for non-equilibrium solution or non-ideal solutions, we've introduced the concept of activity. Activity is defined as the pressure of a component over the pressure whenever it's pure. And when we put it into the chemical potential program, we just see that it replaces Xi for an ideal gas, or for an ideal solution. And that leads us to an activity coefficient. So I have the activity coefficient times the mole fraction is the same as the activity, right? We've pointed out that whenever this activity coefficient is equal to 1, then I have an ideal solution. So the pressures that we observed are the same as Raoult's law would predict, right? The other thing that we're going to apply today, I just wanted to point this out, if we have a situation where I have stronger interactions between my two components of the solution compared to when they're isolated, that leads to, oh, that's backwards. All right, stronger attractive, that leads to an activity coefficient less than 1, all right? And that leads to a pressure less than ideal. All right, that's important to keep in mind. All right, if I have weaker interactions, and I see I have another typo there, that leads to increased vapor pressure over that of ideal, right? And that means that I'm going to have an activity coefficient greater than 1. Okay. All right, so things that we're going to talk today, we're going to finish our discussion of delta G of mixing for a non-ideal solution. We're pretty close at this point. And then we're going to move into a discussion, this is chapter 12, of the equilibrium concept. We're going to introduce the concept of extent of reaction, and then we're going to be using this idea and the equilibrium constant basically to explain Le Chatelier's principle, which you've seen in Chem 178. And one application of that is if I change the volume of a gas phase reaction, that's going to change the pressure, and that impacts where the equilibrium distribution of products or reactants lie. All right, and then we'll see a relationship between the equilibrium constant in terms of pressure and that in terms of molar concentration. I'm not sure we're going to get to this point, but if we do, we're good. All right, things that we're going to do today. We've actually used this already. So the Gibbs energy is the chemical potential times the number of moles. The molar quantity for a component then will be given by xi times the chemical potential when it's pure, and then xi times RT ln of the activity. And we've said that the activity is the same as the mole fraction times the activity coefficient, and I can separate these two terms out because it's the natural log of a product. All right? And then when we get to chapter 12, just a little reminder, we know that the pressure of a component of a gas phase reaction will be the total pressure times the mole fraction of that component in the gas phase. That's going to be the number of moles of that component over the total number of moles times the pressure. We're going to use that today in our derivations. All right, so where we left last time, we were at this point. All right, so for our non-ideal solution, we've got delta G of mixing is given by x times RT ln x for each of the components plus xRT ln of the activity coefficient for each of the components, right? So to make this consistent with delta G of mixing reference to RT, I'm going to divide through by RT, right? And when I do that, I end up with the first two terms, mole fraction times the natural log of the mole fraction, right? And then my second two terms have the activity coefficients, right? Well, we recognize that's exactly the same as delta G mixing ideal, right? So there's no deviation there, right? And that really means that all the non-ideal behavior is contained in here, right? So if I take this portion times RT, we call that the excess Gibbs energy of mixing. All right, and I'm going to define that. I've introduced I've just added a blank page for me to jot a few things down on here. All right, so this GE is equal to x1 RT ln x1 plus x2 RT, whoops, not x1, activity coefficient 1, activity coefficient 2. Okay? So I've just taken this portion, multiplied it by RT. All right? That's our excess Gibbs energy of mixing. Okay? All right, the other thing that we want to just point out is the delta G of mixing then for non-ideal is given by delta G of mixing ideal plus this excess Gibbs energy of mixing. All right? So delta G mixing non-ideal, delta G ideal, and then my Gibbs energy of excess Gibbs energy. Does that make sense? All right. Okay, so let's talk a little bit about some things. If we expect solubility, right? If we expect when I bring the two liquids together, what's delta G of mixing have to be? It's got to be less than 0, okay? All right, so let's talk about what that means whenever we specifically have different types of interactions. So the first interaction that we'll look at is when my activity coefficient is less than 1, right? So when my activity coefficient is less than 1, this means that the pressure that we observe over the solution is less than what we expect for ideal, right? What kind of interactions does that mean that we have in the liquid-liquid solution? Stronger attractive interactions, right? Stronger attractive. All right? And so if that activity coefficient is less than 1, the natural log of that activity coefficient is going to be less than 0. All right? And so in that case, we have delta G mixing ideal is always less than 0. And now we've got the Gibbs excess energy of mixing also less than 0. All right? And so what that says is that when I sum these two together, I get something that is more negative than the ideal situation. All right? And so what that says is that we have an enhanced driving force to dissolve. Does that make sense? All right? So enhanced okay? All right. And basically, because we have the stronger interactions, this is related to attractive interactions. So we'd expect that delta H for this process would release some heat. Okay? All right. right, the other possibility that I can have is that my activity coefficient is greater than 1, and that corresponds to bringing the two liquids together and that having a weaker interaction between the solvent and solute, or the liquid 1 and liquid 2. Right, so weaker, or if you prefer, disruptive interactions. Liquid 1 and liquid 2. Okay? All right. And by the same reasoning, this tells me that the natural log of the activity coefficient under these circumstances is going to be negative or positive. It's going to be positive. It's going to be greater than 0. All right? And that also tells me that the Gibbs energy, the excess Gibbs energy of mixing, is going to be positive. All right? All right? And so that means that we expect that this is going to be opposing spontaneity of mixing, right? Does that make sense? Okay? All right. The other thing we recognize is that this also tells us the situation when we expect to not have solubility, right? If this value is larger than delta G of mixing for an ideal solution, it's not going to dissolve, right? So I can say if GE, and because these are opposite sign, I'm going to take the absolute value is greater than delta G mixing ideal, then I don't have solubility and it's immiscible liquids. All right, does that make sense? All right, and so this is pretty important because this basically explains why not all two liquids dissolve in each other. Oil and water, right? And that's because they have repulsive interactions or disruptive interactions relative to whenever they're pure substances, right? And then the only other one, just for completeness, if our chemical potential, let me put a line in here and a line in there, right? So if it's equal to 1, then we know that means that we have ideal, right? Because the activity is equal to the mole fraction. And what's GE? What's the excess Gibbs energy of mixing then? That's going to be the natural log of 1, right? Which is 0. Okay? Make sense? All right, moving into chapter 12, we're going to talk about chemical equilibrium. All right, and as you know from Gen Chem 2, how many people have taken Chem 211? Anybody? So Chem 211, it's all about equilibrium. And those of you that are in biochemistry, equilibrium is really, really important in biochemical reactions. And those of you that go on into work in petrochemicals or whatever, you need to know where equilibrium lies for any of your processing. All right. And it may not have been clear before, but equilibrium we will show as a consequence of thermodynamics, right? So we're going to introduce a concept that you've seen before, but maybe have not used it the same way that we're planning to, right? And this is called the extent of reaction, all right? And the symbol for that is the Greek letter psi. You can say psi, xi, psi, all right? I'm really horrible at drawing it. That's the Greek letter psi, right? I've gotten better after teaching this 8 times, right? But at first, it used to really slow me down, right? So this is extent of reaction. It can have values between 0 and 1 mole, right? So if I have an extent of reaction 0, that means my reaction goes nowhere. I only have reactants. If my extent of reaction is 1 mole, that means I've gone completely to products and I have no reactants left. Does that make sense? All right. Okay, and then big conceptual portion of this class, if this chapter is at equilibrium, we've minimized the Gibbs energy for the reactants and the products. Okay? All right, so in 12.1, what we're going to do is come up with an expression for Kp, a function of temperature. So that's the equilibrium constant. And does anybody know what this P is referring to? Anybody remember from Gen Chem when that showed up? Right, that's in terms of pressure, all right? All right, and that means that we're going to start by talking about gas phase reactions, all right? So the gas phase reaction that we're going to look at, the symbolism here is, consistent with the textbook, which is annoying. So I've got product A reacting with product B to give me, or reactant A with product with zip, 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 zip. All right, I'm hitting the rewind button. All right, reactant A, reactant B, product Y, product Z. Okay, and then this nu in front is the coefficient from the balanced chemical reaction equation. Okay, all right. And then to make things a little bit less vague, I'm just going to write 2A to A2. And I'm going to refer back to that whenever we talk about some of the equations that we're going to derive from this. Okay? All right, so what we want to do is talk about the moles of the reactants and products that we have in our mixture as a function of the extent of the reaction. All right? So if we think about what that means, if I'm talking about the number of moles of reactants, I'll start with the number of moles of A. So that says the number of moles of A at some time, all right, are going to be given by, well, that has to start with what I initially have present. So we indicate that as Na0, right? And so anytime that you see this little 0 underneath, that just means the initial number of moles. Right? And because it's a reactant, we expect that if the reaction proceeds, that we're going to debit that amount. All right? So this will be minus. All right? So we want it in terms of extent of reaction, so I'm going to put down psi. All right? Okay? So if we think about it in terms of this reaction, right? So let's say I started with 4 moles of A. All right? So that would be 4 minus, right? And then if my extent of reaction is 0 to 1 mole, let's say the extent of the reaction is 1, how many of these am I going to consume? 2 moles, right? Does that make sense? So that means I need to multiply the extent of the reaction by the coefficient from the balanced reaction equation. Okay? So this gives me an expression for the number of moles of A at any time as a function of the extent of the reaction. Right? Same thing here for the number of moles of B, my other reactant. Right? And then we can talk about the products. So for Y, well, that's going to be, again, the initial number of moles of Y. Right? But now I expect that as the reaction proceeds, they're going to be making this material. Right? So that means that I'm going to have a positive sign in here. And again, I need to multiply it by the coefficient from the balanced reaction equation, right? And of course, we've got it for the other product here as well. Okay? Does that make sense? All right, so one of the things that we've seen is that when we use this negative sign, we've been doing it with regards to the reactants, and that's because whenever the reaction's proceeding in the forward direction, we're going to be consuming the reactants. Okay? are consumed, not consuming. Okay? All right, now because what we're really interested in knowing is how the Gibbs energy is going to change with a change in the extent of the reaction. At least we're going to be interested in looking at how the number of moles are changing also. So I need to take the differential of each of these equations, all right? And so if I go dNA, well, we started with 4 moles of this, so the differential of 4 is 0, all right? And nu, so I have minus nu times A, that's a constant. And the only thing I have left to differentiate then is the extent of the reaction, all right? So I've got minus the coefficient from the balanced reaction equation, the change in the extent of reaction, same thing for reactant B, all right? And then for the product, well, that ends up being the same thing, but now it's going to be plus the coefficient from the balanced reaction equation, the change in the extent of the reaction, okay? All right, now we want to do, because we want to talk about spontaneity, spontaneous directions, we're going to go back to the Gibbs energy. And up to this point in time, just very generally, what we know the Gibbs energy of a system depends on is T and P, right? We've talked about that previously. What we're adding now is that it depends on the number of moles of the reactants and the number of moles of the products. All right? And if I want to know how the Gibbs energy changes due to each of these determinants of where the Gibbs energy is, I take a total differential, right? Because we're focused on the chemical reaction itself, that means we're going to stick with the moles. So we're going to hold temperature and pressure constant, and then I do a complete differentiation. So I have the Gibbs energy change due to a change in the number of moles of reactant A times the change in the number of moles of reactant B. Same for reactant A, same thing for reactant B, and then I have my products. Okay? Make sense? All right. And what is dGdN the same as? That's a definition. That's our chemical potential, right? And so that really says that I can rewrite this in terms of chemical potentials. So a chemical potential for product A, chemical potential for reactant B, chemical potential for Y, chemical potential for Z, and there's a spurious equal sign that creeped in there at some point. Not really sure. All right. Now, the other thing that we know that we've just determined is that dN of our components, so that can be a reactant or a product, is going to be equal to plus or minus the coefficient from the balanced chemical reaction equation times the change in the extent of the reaction. Right? And the plus occurs whenever we're talking about products. We're making those. Minus occurs whenever we're talking about reactants. It's just what we've got up above. All right? So for each of these dNs, we can replace them with nu d psi, nu d psi, nu d psi. All right? And one of the things that we see is that in common, we've got the change in the extent of the reaction in every term, so I can pull that out. All right? And then what I can do is I can take dg and divide both sides by the change in the extent of the reaction. So dg de, or dg d psi. Right? So this is Gibbs energy change due to chemical reaction. All right? And if you think about that, that's delta G of the reaction. All right? That's how the Gibbs energy is changing by doing a chemical reaction. Right? And so I'm left with these terms. So I've got chemical potential times the coefficient from the balanced reaction equation for each one of these. Okay? All right. And then the units of delta G of reaction are joules per mole. Right? So I know at some point people were asking, when you write a chemical reaction equation, you write delta H. I'll be with you in a second. You write delta H. Why do you see joules per mole for a reaction that you're not necessarily making 1 mole? That's because it's referencing the extent of reaction. Right? Did you have a?
It gives energy change. The third term supposed to be the chemical potential of Y.
Say that again.
First,
Oh.
you have the chemical potential of Z, obviously.
Chemical potential Z. Oh, yeah. All right. So I have a lot of cut and paste errors. Was there another one?
Yeah, there's
BB. Oh, yeah. All right. Here, I'm going to have you satiate yourself. Let's see. So I've got, this should be Y, Y, Z, Z, BB, Y, Y. At least I'm consistently wrong, right? At any rate, hopefully it makes sense. It's the chemical potential of substance Y times the coefficient from the reaction equation Y. Okay, does that make sense? All right, so at any rate, now we've got an expression for delta G of reaction. Okay? All right, so now what we're going to do is we're going to return to our chemical potentials, right? Keep in mind that what we've got is a gas phase reaction. So the chemical potential for each of the reactants, each of the products, is going to be the chemical potential at 1 bar plus RT ln the pressure reference to 1 bar. Okay? Right? And that's just the chemical potential. And then the Gibbs energy is going to be the chemical potential times the number of moles. So we get the Gibbs energy for each A, B, Y, and Z is going to be given by chemical potential at 1 bar times the coefficient from the balanced reaction equation. And then you see that there's a missing piece here. Right? But I will say I did this on purpose. Right? If I bring this new sub J out front, how can I incorporate it inside of the natural log? It's going to be P over P naught to the new sub J. Okay? Does that make sense? All right? Okay. And so I've got one of these for each of the reactants and each of the products, right? So each of them's got a term at 1 bar. So I've collected those. So this is a product, a reactant, a reactant. All right? And then RT ln P to the new is going to be the same for all of those. Right? So I can bring them all and put them all together. All right? So what I've left out here is the reference. Right? So next to it, I'm going to have, let's see, 1 over P naught to the new Y, 1 over P naught to the new Z, 1 over P naught to the new A, and 1 over P naught to the new B. All right? And if you think about this in terms of what you've done with equilibrium constants before, this basically just makes this unitless within the natural log function. Okay? Make sense? All right, so because this is, if you look at it, this is the Gibbs energy of Y at 1 bar. This is the Gibbs energy of Z at 1 bar. This is the Gibbs energy of A at 1 bar, and this is the Gibbs energy of B at 1 bar. All right? So these are the products, and these are the reactants. So this is the change in the Gibbs energy at 1 bar. All right? Delta G naught. Okay? Does that make sense? All right? So the next thing that we're going to do is we're going to collect the terms within this natural log function, and we're going to call them Q. All right? So that's going to be Py over 1 bar to the new Y, Pz over 1 bar to the new Z, divided by Pa over 1 bar to the new A, and Pb over 1 bar to the nu B. All right? Does anybody remember what we call this ratio of pressures raised to the coefficients from the balanced reaction equations? What's that? It's not the equilibrium constant yet. What is it when it's not at equilibrium? Reaction quotient. Okay? Does that make sense? All right? So this is just any arbitrary time, the ratio of those pressures of the products over the reactants to the appropriate powers. So putting this all together, we can say that delta G of our reaction is going to be delta G of the reaction at 1 bar plus RT ln of Q. All right? So this is the delta G at any conditions. All right? This is at 1 bar for all the reactants and all the products. If I'm at equilibrium with my reaction, what's delta G have to be equal to? It's going to be equal to 0. All right? Right. And so when we say that this is all equal to 0, that's saying that delta G naught plus RT ln the reaction quotient sum to 0. All right? And what I'm going to do is I'm going to rearrange these and say delta G naught, delta RG naught is equal to minus RT ln. And now to indicate that we're at equilibrium, I'm going to replace the reaction quotient with the equilibrium constant. So the little p, again, means it's in terms of pressures, and it's a function of temperature. All right? All right. And this is where we define the equilibrium constant. Okay? All right. So just to avoid lots of clutter, I've left out the reference to 1 bar in this expression and in this expression. All right? But we know at this point that that's going to be unitless when we do the ratio. Okay, so what we're going to do now is we're going to look at the relationship between K as a function of temperature and the extent of a reaction. Okay? All right, so let me talk through this. There's a homework question that follows this, and it can be a little bit difficult. So let's make sure that we get this. So we're going to be talking about PCl5 decomposing to PCl3 and Cl2. So we're saying this is our equilibrium. All right? Now I know that I can write the equilibrium expression in terms of the pressure of my products over the pressure of the reactants. And because this is a 1 mole to 1 mole to 1 mole ratio, I don't have to worry about any other coefficients than 1. Okay? Does that make sense? All right. So, and our goal is to get an expression for the equilibrium constant, K, in terms of extent of reaction. All right? So, and we're going to say that we're going to start with 1 mole of this reactant and none of the product. Okay? All right, so then the question is, at equilibrium, what have I got for the number of moles of each of these? Well, the number of moles of my reactant will be 1, the initial amount, minus the extent of the reaction. All right? Now, if I had 2 moles of this, it would be 2 extent of the reaction. Make sense? All right? And then I look at my products. So if the extent of the reaction at equilibrium is simply going to be the number of moles of PCl3 because I had nothing initially. This is 0 plus the extent of the reaction. All right? And the Cl2 will be exactly the same. Okay? All right. The thing that we want to keep in mind is I need these pressures, and I just want to remind you that what we said at the outset, that the pressure of one of our components is given by the number of moles of that component divided by the total number of moles times the total pressure. Okay? All right, so what I've got right now is the number of moles of each of the components. I need the total number of moles, so that's going to be 1 minus psi plus psi plus psi, and that sums to 1 plus psi at equilibrium. Okay? All right. And that means now that I can write down what the partial pressures are for each of the reactants and products. All right. So that's going to be equal to, for PCl3 and PCl and Cl2, for both of them, it's going to be the extent of the reaction at equilibrium divided by 1 plus the extent of the reaction at equilibrium times the total pressure. And then for PCl5, that's going to be 1 minus the extent of the reaction at equilibrium divided by 1 plus the extent of reaction at equilibrium, the whole thing times the total pressure. That all make sense? All right. So now I have expressions for the pressure of the components in terms of extent of reaction and the total pressure, and that means I can plug those back in for these partial pressures. All right. So for PCl3 and Cl2, I have the same expression in the numerator, right? PCl3, PCl2, partial pressure of each. And then the denominator, I've got this expression for the product, or for the reactant. All right. All right. So we can do a little bit of simplification to this. So one thing that we see is that we've got pressure showing up in two places. All right. I also have 1 plus the extent of reaction in the denominator in two places. Right? What that leaves me with is total pressure, extent of reaction, so that's squared. And then I've got in the denominator 1 plus the extent of the reaction times 1 minus the extent of the reaction. That gets me 1 minus the extent of the reaction. Does that make sense? Okay? All right, so let's focus on this. All right? So our equilibrium constant is a constant. All right? Let's say that I take the volume and decrease it. What does that do to the pressure of the system? The pressure goes up. All right? If pressure goes up, for this to stay constant, what has to happen to the extent of the reaction? It has to go down. Okay? So we can say, therefore, extent of reaction at equilibrium goes down. Okay? All right? And of course, by the same token, if we increase the volume, the pressure goes down, and the extent of the reaction has to go up. Right? Make sense? All right. So you may recall, this is, if we look at this, we can think of this in terms of Le Chatelier's principle. I have 1 mole, I have 2 moles of gas. Right? If I increase the pressure by decreasing the volume, the stress on the system is that I'm increasing the concentration. So it's going to react to try to reduce that. All right? If I reduce the pressure, then the reactions go in the forward direction because it's going to try to compensate for that. All right? Does that make sense? And that's what we say down here. Chemical reaction at equilibrium, change of condition displaces it. The reaction adjusts to try to offset. All right? The other way that we can look at this is that this equation that we've derived can be plotted with the extent of the reaction as a function of the pressure. Okay? And this basically says, if I have this situation where I start with 1 mole of the reactant and I'm sitting at 100 bar, that's where the extent of the reaction is going to be. All right? Okay. And then if I deviate from that, let's say I change the pressure to 50, which means I'm going to increase the volume. I'm going to instantaneously be here, and then it's going to try to get back to that line. All right? Alternatively, I could start here at equilibrium, increase the pressure by decreasing the volume, and then it's going to come back to this line. All right? And the general trend that we see for what we've talked about is if I want to maximize the formation of product, if I want to make more, I'm going to keep making the volume bigger and reducing the pressure. That drives the reaction forward. If I want to go back towards reactants, I'm going to increase the pressure. Make sense? Okay? All right. The other thing to mention, I'm not going to go through this, but if I flip that reaction direction, right, that flips my equilibrium constant. And then everything that we've said is simply going to be reversed. Right? The stress on the system would cause us to try to get the product. We're going to be increasing. Now I've confused myself. If I flip it, I'm going to want to be decreasing the pressure. Okay? Does that make sense? All right, so the next thing that we want to do is talk about how we can write the equilibrium constant in terms of molar concentration. And that's probably what you're most familiar with from Gen Chem. All right? So we've derived the equilibrium constant in terms of pressure, so Kp, and what we want to do is get it in terms of molar concentration. Right? So what we're going to do is we're going to start with our ideal gas law, right? And we know that molar concentration is N over V, all right? And so if I start with my ideal gas law and divide both sides by V, that gets me the concentration here, and I can say that the pressure is given by the concentration, the molar concentration times RT, right? Getting rid of that equal sign there, all right? Okay, so putting this in for each of the individual pressures is what's going to get us the equilibrium constant in terms of Kc, right? So I'm going to put CRT for each of my components. So there's Y, and there's a whole mess of typos in here too. So let's fix those. So I've got RT times the concentration of Y, that's correct. And then I have to put Z in, and then I have to put A in, and then I have to put B in, all right? And then I still have these reference to 1 bar for each of these components, all right? We good? Okay. All right, and then the next thing that we do is we say, well, if I pull out the RTs, which is what I've done here, I pull out the RTs, that's going to be raised to the VZ plus VY minus VA minus VB, so that's this. So that's the RTs. They all come back into this term, all right? So you see that I've introduced a C naught in here. That's 1 molar, all right? And the way that we get to that is we basically say, I've got this in terms of concentration. I can divide it by concentration here, and that means I need to multiply by concentration to make it multiplying by 1. So that gives me C naughts here and C naughts there. We good? Make sense? All right, so that's Kc, right? And that basically tells me that this is the conversion factor that gets me between the equilibrium constants in terms of pressure and molar concentration. All right? So let's do a quick... actually, let's do this. What time is it? And it's 10:47. Do you guys have a spare piece of paper? Why don't you guys do this? That'll be your quiz. Put your name on a piece of paper. You can work in groups of how many ever are at a table. Because I've been talking too much today. And if anybody needs paper, I've got spare. Right? Do you need paper? Okay. And I'll start working on it too. I just will shut up. All right, let me talk this through a little bit. So Kc equals Kp. We've got that up above. And then I take the reciprocal of the conversion factor. So I've got 1 bar over 1 mole per decimeter cubed or liter, R and T. So P naught is 1 bar. That's our reference. And then for concentration, it's 1 mole per liter or 1 mole per decimeter cubed. That tells us which R to use, 0.08314 bar decimeter cubed per mole K. Needed to convert to 573 Kelvin. And when you work out all the arithmetic, you end up with 9.62. That's where we're going to leave it for today. Have a good one. We will see you on Wednesday.